Okay, hi everyone, welcome back. More question and answers. I have still been asked about this difference between stochastic and Stratonovich calculus, and I decided to add one piece of detail that normally I I don't give, uh, but just as a response to a question. Uh, in the class, we mentioned the problem of defining uh, the meaning of a differential equation in the presence of a stochastic force that is never differentiable. And we mentioned the possibility of discretizing this in different conventions. And without being too general, uh, and consider the general case in which also D depends on the position, which will generate several complications. Let's stick to the minimum basis and let's provide explicitly two ways in which you can actually connect, you can actually give a meaning to this equation. One is the Ito rule that we already discussed, and I will rewrite it here in the following way. It takes basically no time for you to realize that this is equivalent to the Langevin equation. I just shuffled the terms differently, bringing the stochastic noise on the right hand side and everything else on the left hand side, and express the D as a KT over gamma or M gamma. Let's see. You can define this way or with an M right here, depends on what is your definition of gamma. I think in the paper, in the rest of the course, I used M gamma. So let's put M gamma here. That's the Ito rule. The Stratonovich rule, to be quite explicit, is looking the same as far as this part is concerned. But instead of taking the force at the previous time, you evaluate it at average between the previous time and the later time. Now, these are two pretty legitimate discretization rules. This is the Ito one. This is the Stratonovich one. Now, if you follow up with this, and you can define two different calculus, and it turns out that the Ito fundamental theorem of calculus is different from the normal one. On the other hand, the Stratonovich fundamental theorem of calculus is the same as the normal one. So where does the second derivative in the action comes from if the Stratonovich fundamental theorem of calculus is the same? Remember, the second derivative in the Onsager-Markov option comes from applying plus. I don't quite remember if it's a plus. I think it's a plus. I should actually go and check on this sign here. Don't have my notes with me, but anyway. For Ito integrals. And this is a normal integral. Now, the statement that I've just made and didn't prove is that the Stratonovich calculus has a normal fundamental theorem of calculus. So where does the second, since we want the both calculations, the both approaches, I made a statement in my previous question and answer, that both approaches lead to the same dynamics. So it's just a freedom we have that doesn't affect physics. And the dynamics includes the second derivative. Where does the second derivative come from? And the answer is it comes from the Jacobian of this transformation. When you insert, remember how we in order to evaluate the path integral, we first consider the probability of having n random noises sampled, and then use this equation to translate this information into information concerning the path that is determined by these sequences of random noises. And in the case of Ito, the Jacobian of this change of variable here is actually 1, but the fundamental theorem of calculus is non-trivial. In case of Stratonovich, the fundamental theorem of calculus is trivial, but the Jacobian is not 1, and the Jacobian provides exactly the second derivative term that is needed to get a right action in the exponent. So in the end, since you have the same path integral for the same probability, you prove that both methods lead to the same dynamics and same distribution probability at any time. So they're completely equivalent. I want to just say that you can find a discussion about this and the calculation of the Jacobian in a paper. I won't do it in the course. I think it's a little bit too technical. I want to suggest this paper by Ron Albor, David Shalloway, and I think it's it. And it's on the Journal of Chemical Physics. Uh, 112 and let's see, it's my notes here. Page 539, published in year 2000, when I was still a PhD student. Okay, Shalloway. If you're interested to learn more, go and read this paper, and you find interesting information, and you basically get all the calculations. That's where I got my derivation of the path integral from. I think it's the most instructive one. Thank you. Bye-bye.